The synchrotron Elettra and the free electron laser Fermi are two international light source facilities which accept users from both academic institutions and industry. The laboratory provides the means for investigation of material properties down to the atomic length scale, using a wide range of experimental techniques, including powerful microscopy methods. Among these, X-ray spectral microscopy offers a powerful tool for analyzing matter at the micron and submicron scale. High spatial resolution, based on the short X-ray wavelengths, deep penetration, and the elemental sensitivity of X-rays, give X-ray microscopy a great advantage over comparable microscopy techniques.
The TwinMic microscope was designed and constructed between 2001 and 2004 through an European project that gathered together European scientists with the highest expertise in X-ray microscopy, X-ray optics and X-rays in general. It's an instrument highly modular in its optical configuration and it provides a versatile specimen environment. The TwinMic beamline was instead built in 2006 and was opened to users in 2007, after only 10 months of construction. The soft X-ray beamline hosts a unique short undulator source and covers the energy range between 400 and 2200 dB. TwinMic integrates in a single instrument the advantages of complementary scanning and full-field imaging mode. The full-field mode is the analogous of the visible light transmission microscope, where a condenser lens illuminates the sample and an objective lens creates a magnified image of the sample. In the case of soft X-rays, the objective lens is a zone plate that can provide a spatial resolution of 20-30 nanometers.
In the scanning transmission mode, the beam is focused on the sample by another zone plate, and the transmitted X-rays are collected by a CCD, providing simultaneously absorption and phase contrast images. The spatial resolution can range from 1.5 micrometers to 50 nanometers. In 2008, we started developing the first worldwide low-energy X-ray fluorescence system, coupled with the scanning transmission mode. The setup, 8 silicon drift detectors facing the sample, was finalized in 2010. In addition to X-ray fluorescence, we perform X-ray absorption spectroscopy, in particular on transition metals.
X-ray spectral microscopy finds application in a wide range of scientific investigations. The TwinMic beamline, in fact, has attracted the interest of several life science communities. For instance, we investigated the mechanism underlying metal ion accumulation, distribution, storage and bioavailability in Witaleoron subcellular organelles. Low-energy X-ray fluorescence allowed us to identify subcellular distribution of physiologically important elements such as zinc, iron, sodium, magnesium, aluminium, silicon and phosphor. Recently, the combination of low-energy X-ray fluorescence and microimaging revealed unexpected formation mechanisms of asbestos bodies in lung tissues by analyzing the correlation of magnesium and iron in combination with lighter elements, in particular oxygen.
At the TwinMic beamline, we have had a long-term collaboration with the University of Salento on fuel cells and batteries, where we have been studying and analyzing electrochemical systems made with different materials and electrolytes. X-ray imaging, X-ray fluorescence and X-ray absorption spectroscopy combined in this single instrument allowed us to investigate electrodeposition and corrosion of metals in the presence of liquid or ionic liquid electrolytes.
Recently in TwinMic we tested an innovative X-ray imaging method called Ptychography. Ptychography is evolving rapidly into an important X-ray imaging tool. It can be performed with X-ray optics or as a lensless imaging mode, and in both cases it can provide a spatial resolution better than the limit imposed by the system. The technique involves successively illuminating overlapping regions of a specimen with a coherent probe and recording the resulting diffraction patterns. It is important that the illuminated areas overlap significantly, since those common regions provide duplicate information that allows computer algorithms to reconstruct reliably both the sample transmission function and the illuminating probe.
Not only we provide our users with assistance during the experiment, but also we facilitate the analysis of the acquired data, both spectroscopy and imaging. This is done with the help of the Elettra scientific computing team, a team integrated in various beamline activities and composed by specialists in computational mathematics and imaging. Additional activities of this team for TwinMic include end-station control systems for data acquisition and supercomputing infrastructure for data computation and storage.
The TwinMic beamline can be accessed by submitting an experiment proposal to the Elettra review panel. The beamline personnel can be contacted for further details.